Every single time I hear the news of someone passing away from cancer, the only question I can come to ask myself is, why is there no cure yet? I mean, these diseases have been the front of attention for a while now, and they've had billions of dollars and countless hours invested into them so that a cure can be found. And this doesn't apply to just cancer. Dementia, Alzheimer's disease, heart and liver diseases, you name it. All these super complex conditions that can take over our lives in a snap. And seeing how commonly they affect someone doesn't help either. When I was trying to answer this question for myself, I went down this rabbit hole of reading articles and papers, and that's when I came across this alarming fact, that it takes a minimum of 10 years and around $2.6 billion to research and develop a successful drug. It's insane. 10 years doesn't sound like a long period of time, but when I put it in the context of being more than half of my age, I knew it was a problem. If the entire drug discovery industry is all about designing and optimizing new drug candidates that can treat a range of diseases. But at its core, scientists are basically studying the interactions between molecules. The main question that's being asked beyond all of this is if two or more molecules interact with each other, is it safe or harmful? And I hate to be just like your grade 9 chemistry teacher, but the properties of the molecules that you're working with pretty much dictate the reactions that'll happen. And this is one of the bigger problems that exists within that 10-year timeline. Within a molecule, in order to figure out the properties that we need to know for its interactions, we need some information on the molecule's energies. But it's actually just one number that we're looking for. And when I tell you that the process to determine this one number is not simple or easy, I genuinely mean it. For some context, molecules have different energy levels, like almost everything around us. They can be more excited at times, and they can be less excited. But there's a ground state, which is the least excited state, in which we can figure out all the properties we need to know about a molecule for its interactions. But the problem is, when there's millions or thousands of different potential energies to look between, calculating for the smallest one is not the easiest solution. Even with recent advancements in technologies over the year, it's still a challenge. For a complex molecule, the time needed can range anywhere from 6 months to 4 to 5 years. And the fact that this is one of the first steps in the drug discovery process doesn't help, as it makes that entire 10-year framework extremely inefficient. But there actually is a way to streamline this inefficient process down to 5 years, and also reduce that billion-dollar cost into the millions. And it's known as the variational quantum eigensolver. It's the key to calculating the ground state of a molecule. But let's break the solution down to fully understand what's going on. And we'll start with the word quantum. Quantum computers, if you've never heard of them before, are basically a special kind of computers that are 10 times faster than our traditional computers that we use right now. And this is done through leveraging quantum physics and the powers of them, and also based on the representation of our data. The computers that we use every single day use a data type called bits, and essentially all of our information is represented through a bunch of zeros and ones. Quantum computers, on the other hand, leverage a power from quantum physics called superposition, which means that our data can exist in between 0 and 1 at the exact same time. But if computer language makes zero sense to you, I'm sure that my favorite image to explain superposition will. I'm sure we've all seen the infamous meme of the student writing his answer in a way that it can be described as both true and false at the exact same time. And that's basically what superposition is. It's pretty genius, right? It enables the calculation of two problems at one time, which allows for an exponential speed up in comparison to our classical computers. And that time reduction is exactly what we're looking for within the drug discovery industry. But the true solution actually lies within the eigensolver itself, as it's what can find what's known as the eigenvalue of a matrix, which is basically a fancy math term for the lowest value. And this is done through a mathematical array of numbers, which is formally called a Hamiltonian matrix. All the numbers within our matrix are basically our potential molecular energies that we have to find the eigenvalue of. And we do this through our friend, the variational quantum eigensolver, also known as a VQE. The first piece of information that our VQE wants to know about is our molecular Hamiltonian. So basically that mathematical array of numbers and energies that we just talked about. This is done through applying a mathematical transformation on the geometric structure of the molecule known as the Born-Oppenheimer approximation. Once we've got that, we can go ahead and create a trial ground state. This is basically just an initial guess that's used as an input into the quantum computer to get closer to our ground state. The main goal of this is to create a ground state that is closer to the actual value, even if it isn't the exact value itself. Once we've got that approximate value, we can optimize our circuit to reduce down this number further. And this involves using a classical optimization algorithm to reiterate on all the parameters that are set in place within the quantum computer to get to its minimum value. And we know that we've reached the minimum value when the quantum computer finishes outputting the energy values of the system, and we see that a number repeats. When I was actually reading about this first step, though, my number one thought was invalid guesses. I was so concerned about the fact that our circuit could reiterate on its parameters, and we would reach a state in which the quantum computer outputs invalid guesses, as it could be lower than the actual ground state itself. But this fancy equation is actually responsible for eliminating all of my fears. It's known as the variational principle. It's the backbone behind the working of our VQEs. All it really states behind these complex symbols is that any guess within our Hamiltonian matrix will always be greater than or equal to the true ground state value. Here, where I built a simulation of a VQE for a hydrogen molecule, you can see that the values get lower and lower each time with each reiteration, until it reaches the final value at step 18 of around negative 1.27. And when I was initially calculating this, I was ready to sit back with my cup of coffee and wait for my computer to compute. But it was actually only a couple of steps in until I got my final ground state. What I'm really trying to get at here is that it ran a lot faster than I was anticipating. And even though I built my molecule for one of the more simpler molecules, on average, humans would need a couple of years to figure out all of these calculations, which it's extremely inefficient to that drug discovery timeline that we talked about. Our classical computers are a little bit better. They can take up to a few months to figure out all of these calculations. And even though it's a little bit longer than we traditionally want, it's still better than that year's timeline. But our quantum computers are the true hero, as they can reduce this number down to a matter of days and give us our ground state and create the entire drug discovery timeline into one that's both efficient and organized. As we reach the full development of quantum computing, we can enter the next era of drug discovery where we can get closer to the cure of our diseases through an organized manner.